Okay, well, let's get started. Topic today is linear and nonlinear models. And so I want to, of course, start out with talking about linear models, general linear and then generalized linear models. We'll talk a little bit about interactions and the meaning of those, how to interpret them. We'll look at fixed effects and multivariate models. And then the latter part of the time, we'll look at nonlinear models. And there's actually two different ways of modeling nonlinear functions. We can either model it linearly with what that means is that the models are linear in the parameters. And then we have nonlinear models where the parameters are, where the models coefficients are actually nonlinear in the parameters. Now I'll give some examples of those. Okay, so the general linear model, or GLM, is just a linear regression model. In the simplest case, it's just an outcome variable y, and then that's modeled as a function of a constant and then a single covariate or predictor variable. And so, of course, as you probably all know, the meaning of this is that the constant beta 0 is the value of y when x equals 0. In some instances, for example, if x is age, then a value of 0 may not have any meaning. So sometimes we center x, meaning that we subtract each, the value of each individual from the mean of all individuals. And so in that case, then 0 is the mean. For example, if x was age, it'd be the mean age. And of course, we interpret this as the regression coefficient is the change in y for every unit increase in the predictor variable. And the predictor variable, the regression coefficient, can be either positive or negative. And then multiple linear regression is just a extension of that, where we have more than one covariate, more than one predictor variable. And in this case, the regression coefficients, the betas, are adjusted for all other variables in the model. So for example, the regression coefficient you get for beta sub 1 is adjusted for beta sub 2, 3, and so on, however many you have. And we refer to this as multivariable linear regression. And later on, I'll talk about what we mean by multivariate regression, because they're technically not the same thing. So I have an example here of 25 patients where we have values for each on cholesterol, weight, and age. And so we might want to ask the question, does weight or age predict cholesterol? Or can we model cholesterol as a function as weight and age? And so if we do our regression where we model cholesterol as a function of just age, we get an output like this. This is Stata output, but it'll look similar in SAS or SPSS or whatever software you're using. And so we have our coefficient for age, 5.3, and then our constant, 102. So if we haven't centered age, then this means that the cholesterol value is 102 when age is equal to 0, but that's not terribly meaningful here. And then the age coefficient, 5.3, means that for every unit increase in age, cholesterol increases by 5.3 units. And then we also have some important information here that tells us the overall statistical analysis in terms of a p-value. And then the R squared or adjusted R squared. Adjusted R squared is just adjusting for the number of subjects or patients in the model. It will always be slightly less or maybe a lot less than the R squared, depending on how many patients you have. But you can see in this case that our R squared value is 0.7. So what this means is that 70% of the variability in cholesterol is accounted for by age. And so we would write our formula to look like this. Cholesterol equals 102.6 plus 5.3 times age. So we can get a predicted value for each subject's age. And so if we plot our data and put in our regression line, it would look like this, where the dots are the observed points for each patient of age with their cholesterol level. And then, of course, the straight line is our fitted values are from our regression equation. And then also we would typically include confidence intervals around the regression line. And so here's a 95% confidence interval for the regression line. You can see that at the ends or the low and high values that the regression lines are a bit wider than they are in the middle. And what this indicates is that your best prediction is around the mean of your covariate here, in this case, age. So we can model a multivariable kind of equation here where we have age and weight. And also we might want to investigate whether there's an interaction between age and weight. And what we mean by an interaction is that the values at one level of one of the covariates is not the same across all levels of the other covariate. I'll illustrate this in a bit here. But so here is our model for weight plus age plus the interaction of weight and age. And so you can see that the interaction, the weight by age, is not statistically significant. And so in this case, what we typically do is if an interaction is not statistically significant, we remove it from the model. And in this case, we would just model weight and age. And then we have, of course, our squared value here, which you can see it doesn't change very much from when we just had age in there, which if we carried this out and looked at weight, we'd find that it's not statistically significant either. So our best model is just cholesterol as a function of age. So as I mentioned, an interaction means that the effects of one independent variable or one covariate are not the same across levels of another. If we have no interaction, then that's referred to as main effects. So in the previous example, we had a main effect of age. And we have a couple kinds of interactions called an ordinal or disordinal interaction. And this sort of illustrates the two, where the parallel lines are, that means there's no interaction. The ordinal interaction is where, say, if you have two groups or whatever you're comparing here, start out at more or less the same place and then diverge. The disordinal interaction means that they start out at different places at the beginning and at the end. So here we want to test the hypothesis of the effect of a drug that's been given, let us call it drug A or drug B, on diastolic blood pressure. And because this is a non-randomized study, then we might need to include some covariates that, because the result of the drug might vary with age or with sex. But a research hypothesis and the null hypothesis are just as we would have in typical hypothesis testing, that there's no difference between drug A and drug B as far as lowering blood pressure. So, as I mentioned, because the study is non-randomized, then we have a potential for selection bias. Now, if the study was randomized, then we could just do a simple t-test, because if we had randomized, then the effect of covariates would be canceled out because of the randomization procedure. But in this case, since we have a non-randomized study, then we're going to include potential confounders. For example, are drug A patients older than drug B patients? Or is the sex differential or different between the two drug groups? And so in this example, I'm going to regress blood pressure on the drug, of course, which is our main interest here, but we also are going to include age and sex, and then we're going to include the interactions of drug by age and drug by sex. So if we just look at the distribution in our data of our covariates, we can see that drug A has more females than drug B, and then drug B has a few more males than drug A. So there's a difference there that might indicate that the male female might make a difference in our outcome variable. But the big one that we see here, or the most important one we see, is the difference in age between the two groups. Drug A is about 8 years older on average than the patients in drug A, or drug B is about 8 years older than drug A. So that sort of would clue us to that probably age may be an important or a confounding factor. And so this is our model when we run. So we can see here that we do have a drug by age interaction that is statistically significant. So what this means is that rather than being able to interpret the main effects of drug and sex independently, we can't do that because there's an interaction between drug and age. And so we're going to have to interpret the interaction. And then we have here our observed values, blood pressure values between the two groups. And so we can see that group A appears to be better as far as lowering blood pressure than group B, 70 versus 82. But if we look at the interaction here of drug and sex, we can see the difference. So drug A for females at age 50 is 67. That's the adjusted from the model. In drug B, females at any age is 80. So there's quite a bit of difference here that looks like we have not only a difference by sex, but it's also a difference in ages. And so when you put it in tables, it's sometimes a little hard to see. So what we typically do is plot the adjusted means. And so here we can see the interaction more clearly, where for females, there is they have an increasing blood pressure, or the blood pressure is increasing with age for drug A, but for drug B, it's the same across all age levels, but it's quite a bit higher for drug B. And for males, you get the same sort of pattern there, that for drug A, there is also an increasing blood pressure blood pressure increases with increasing age, but males are at a higher level than females. And then for drug B, you see the same thing. There's no difference in change of blood pressure with increasing age. But again, males have a higher blood pressure than females, even in drug B. So this tells us that we can conclude that drug A is better than drug B, but there's a difference between males and females as far as the effect goes. So that's why we have that interaction. So you can see that when you when you have significant interactions in a model, that it gets a lot more complicated than if you just have significant main effects and no significant interaction. So we then apply linear models to what we call mixed effects models, where we have fixed effects and random effects. And so the fixed effects are attributable to a finite set of levels of a factor or variable. So for example, treatment, sex, age, race, those would all be examples of fixed effects. Random effects are attributable to an infinite set of levels of a factor, of which only a random sample appear in the data. Maybe it's not exactly random, but that's the idea. And so examples of this would be like clinical trial sites, geographic regions, hospitals. Patients, subjects are always a random effect. And so these data are what we call hierarchical or clustered. Repeated measures is probably the most common example of a mixed effects model, because you have repeated measures on the same patient over time. And then if you come across the term variance component, that's talking about the variance of a random effect. And so here's an example from the Courage trial from some years ago, where we have random effects for healthcare system, the US non-VA Canadian healthcare system, and then the VA healthcare system. And then within each healthcare system, we have different sites. So these might be participating hospitals, and they're obviously for each one, there's more than two, but just for sake of illustration here. And then at each site, we have a number of patients that have been enrolled in the study. And these have been then randomly assigned to a treatment, PCI, percutaneous coronary intervention, or OMT, optimal medical therapy. And so our outcome in this case was a quality of life measure, the Seattle Angina Questionnaire, or the SAC. And so we're modeling that as therapy, PCI versus OMT, plus we have follow-up time, and then we have the random effect of healthcare system. We have the random effect of patients within sites within healthcare systems. So it becomes a little bit more complex, but the interpretation is really the same. We're going to have see whether there's a change, whether the change in the Seattle questionnaire, Seattle Angina Questionnaire over time is different between the two therapy groups. And so this is a plot of the means at each time point that we get for each treatment group. And so you can sort of see the trends here that for each of the four of the components of the Seattle Angina Questionnaire, they have physical limitation, angina stability, angina frequency, and quality of life. And so you can see that the PCI generally is doing better early in a short run after treatment has been applied, but over a longer period of time, you can see that the two groups don't differ that much. So this is an example of a mixed effects model where we have included the variance of the healthcare system, the site, and then of course patients. Okay, and now let me talk a little bit about what we call multivariate analysis of variance. And this is different from multivariable analysis of variance, or multivariable linear regression. Sometimes in the literature, you see that the terms will be used interchangeably, but technically there's a difference between the two. And a specific analysis here that's often used is what we call profile analysis. And so in this study, in the example I have here, we have microvalve patients, and we want to compare microvalve repair versus replacement. And we want to compare them with respect to the SF36, or I think now it's probably the SF12 is more commonly used. But anyway, so we have in our outcome variable, we have 8 domains, physical function, and there's some others here, I haven't what they are in the next slide. But what we want to do in a multivariate analysis, we want to test for a profile by group interaction. And then if the interaction is not significant, then we can interpret the group main effects as a difference between profiles. And so this is the SF36, where we have a physical component. So there's physical function, role, physical, bodily pain, and general health, and a mental component composed of mental health, role, emotional, social function, and vitality, 4 different domains. So these are the 4 component, or the 8 components that we want to use as our outcome variable. So this is just the word descriptions of the SF36 domains, the 8 of them. And so we're going to look at the SF-36 as a measure of quality of life. But at the bottom here, I have the model. And so you can see the difference here, where on the left-hand side, I no longer have just a single variable. And what I have here is representing the multivariable matrix of the 8 domains of the SS36. And so we're then modeling that as a function of or mitral valve repair or versus replacement plus follow-up time. And then of course U here is representing our random effects. So this is the plot of the analysis where there was a significant interaction between a group and the and time in this case. And so we can see here that at baseline, the two profiles are pretty similar. That is, they're parallel here. Now that means that there'd be no interaction at baseline here. The replacement group is not doing quite as well as the repair group, and that sort of holds for 1 year post-surgery as well. So we're it's not quite as nice as in the baseline here, but basically the profiles are still parallel. But they're slightly higher than they were at baseline, as you can see. Then at 4 or more years post-surgery, we can see that there's virtually no difference between the two mitral valve repair or replacement, that the profiles are essentially identical. So they would still be parallel, but you can see that we have a sort of a trend over time here of higher domain scores over time for both groups. It's just at the 4+ years post-surgery that there's really no difference in the profiles between the two groups. Okay, so let's turn to nonlinear models and look at the relationship between an outcome and a covariate or set of covariates that is nonlinear. And we can apply this both to regular linear regression as well as logistic regression as well. And so there's 2 different ways of going about this. The most used one, and the one that's easier to use, is basically a linear solution to nonlinear models. And what we mean by a linear solution is that the parameters are linear. And so examples of this, I'm going to go over polynomial regression, fractional polynomial regression, and then splines or piecewise regression. And then, as I put in quotes here, not real, but we're going to actually do a nonlinear model where the parameters are nonlinear. So here's some examples of what might happen when we have nonlinear relationships. And so if we do a linear regression on the top left panel here, we can see that we would get a regression coefficient that's near 0. But of course, in linear terms, that means that there's no relationship between the two, but you can see there's obviously a nonlinear or curvilinear relationship between the two variables. And the same in the bottom left panel here, where if we model this as linear, we're going to get something quite different than we do if we model it as nonlinear. And then in the panel on the right-hand side here, we can see that we have a linear model, which looks like it might be okay, but the question would be, would this be a better model? Would it fit the data better than the linear model? And so we can answer that question. But when you see plots in the literature where they've modeled it as linear, you kind of want to pay attention to the points in the plot, whether they actually seem to be linear, where linear is the best, or maybe not the best model. Oops. Oops. Yeah, there we go. Oh, that went backwards, didn't it? There we go. Okay, so the first example I want to look at is a study of pregnancy-induced hypertension, and that's our outcome, which is either yes or no. So we're going to model it with a logistic regression. And so we have a number of risk factors, age, chronic hypertension, parity, diabetes, et cetera. As I mentioned, our outcome is either a yes or no, a dichotomous variable. But we need to ask, is there a linear relationship between the risk factors and the outcome? And so we think that maybe they might be, but when it comes to BMI, that maybe that's not linear. And so we're going to use polynomial regression in this case to assess linearity. And so polynomial regression uses integers. And so this is the nonlinear part of our model here for BMI, where BMI, that's linear. BMI squared is the quadratic term, and BMI cubed is the cubic term. So we're going to look at BMI as being nonlinear in our model. So these are then the adjusted odds ratios from the model, where we've included chronic hypertension, which is really a strong predictor, which is not too surprising. I actually sort of argued with him about including that because it would seem highly related to pregnancy-induced hypertension, but be that as it may, we can see then there's a strong relationship here with parity, in that null parity has about twice the odds of pregnancy-induced hypertension compared to multi-parity. And then this is diabetes, race. And then you can see here that for BMI, we have some difference here as far as the odds ratios related to different BMI categories. And so we can see here that the reference here is normal BMI, basically 18 to 25. Then these that are underweight, and then these that are overweight, and you can see that there's an increasing odds with increasing BMI, which sort of clues us to the fact that it's nonlinear. And so as an example here, taking the parity categories and plotting those two categories with the probability of pregnancy-induced hypertension with BMI, we can see the nonlinear effect here of BMI. And so for both groups, it appears to be pretty linear up to about a BMI of probably about 40. And then after that, basically the slope of the line changes. And you can see then that it's not the same slope for nulliparity versus multiparity. That for nulliparity, it's even though it's slightly lower than at the beginning, it's still increasing at a faster rate. The probability is increasing at a faster rate than it is for the multiparity patients. Okay, so that's using polynomial regression, where we're using just integers, raising the the covariate to different integer powers. So fractional polynomial is more complicated in the sense of how it's calculated, and I've given kind of a sort of a detailed explanation here. I won't really go into that, but basically what this fractional polynomial means is that instead of integer powers, we're going to use fractional powers, or potentially use them. And so our example here is from a study of the effect of workloads for resident physicians and nurses in a hospitalist program. And so our variables that we're interested in here are age, sex, race, patient illness severity, months from start of this study, and then hospital occupancy. And our outcome variable is going to be hospital length of stay. And again, you can see that this is over the study, 44 physicians billed 20,000 some hospitalizations. So we do have a random effect here of physicians, because these are not the same. You don't have the same physician billing 20,000 patients. So in running our model, this is what we come up with for our final model is in terms of the powers. And so you can see that census here, power of 1 indicates it's just linear. It has, it's basically the census is raised to the power of 1, so it's the same. Age, however, is not. It has powers of it has two different coefficients and powers of 3, which I'll illustrate here. Female, non-white, and hospital occupancy are all linear, but patient illness severity and study entry are nonlinear. And so you can see here that we have most of these are integer, but here we have a fraction where we're going to raise the covariate to that particular power minus 0.5. And so this is what our regression coefficients and then the variable transformation that is made. So census here is census minus this constant. Age here, which was nonlinear, we have age cubed, and then we have age cubed times the log of age, and then we have these constants out here that are determined by the model. Then female, non-white with linear. Patient severity, then we have patient severity raised to the minus 2 power, and then patient severity raised to the minus 0.5 power. Okay, and then occupancy, turns out to be linear. And then study entry has a linear component and then a quadratic component. So that study entry is nonlinear. So when we write out our regression equation, it's going to come out pretty nasty. But anyway, looking at a couple of examples here of the nonlinearity, we've plotted in this case the hazard rate. In other words, that's over time the length of stay in the hospital being the outcome here. And then different levels of occupancy. And so you can see that the hazard rate goes up dramatically when length of stay is 20 some days, but more so when occupancy is between 75% and 85%. And then here is length of stay against the hospital census. And again, you can see for the different levels of occupancy that they're all pretty linear up until about somewhere in here. And then the length of stay increases regardless of hospital occupancy. Okay, so that's an example of plotting some points using oops, here. Oh, okay. So these are the conclusions that that we made from the results of the analysis, where census and occupancy were linear related to length of stay, low occupancy associated with longer length of stay, higher with shorter length of stay, and then increasing physician workload associated with longer length of stay. So another application here of fractional polynomial regression is, say you have, in this case, this is CTM3 is I think like a self-report measure. And so what is plotted here are the means at each quarter. And so what we've done then with just using these data points, applied fractional polynomial regression, and we get a smoothed function of the relationship or the change in scores over time. And so this points out a consideration when you have nonlinear functions is how smooth do you want to make it, or how much bias do you want to tolerate. And so if we can do a model where we can actually get the points here, but this function would be what we would call highly overfitted, whereas our smooth function here is sort of a better representation of the overall trend. But then the question is, how smooth do you want to make your function? Okay, then another way, our last linear way of looking at nonlinear relationships is to do what we call spline functions. And there's different ones here, but because of time, I'm going to just do an example here. So linear spines is basically this idea where we model a nonlinear function with piecewise linear functions. So it's the point here between the start in A and A to B and B to C and C to the end are, you can see, are linear, but overall we have a nonlinear relationship. And the points at which there's a change basically in slope are referred to as knots. And so basically our regression equation comes into play here when we model our knots in here, where we have, if we have just a simple regression here where we have one covariate x, then we have x minus a, x minus b, and x minus c, where they equal the whatever the x minus a is if this is positive, otherwise they're zero. And the drawback to just linear spines is that they may not fit functions that are, highly curved. So like in the example I had before this, it was fairly straightforward, but we might have a relationship that's more complicated than that. And so the alternative to just doing linear splines is what's referred to as cubic spines. I won't go into the details here. You can look at these, later on and on your own. And then cubic splines are what is typically used. So it gives actually a cubic spline actually gives a better fit than just cubic splines. But this is basically the same idea where you have a one covariate, then you are going to square it for the cubic or for the quadratic for the cubic, and then the splines being raised to the third power here, x minus a, x minus b, and x minus c. Okay, and then restricted cubic splines. Basically, the difference here is that they're constrained to be linear in the tails. So and this is just the model, which I won't spend any time on going over. But basically, this is the importance here when you do splines is how many knots is more important than where they are. Basically, I found that 3, 4, or 5 knots are most of the time are sufficient for modeling a nonlinear function. And this is just if you use quantiles, so if you have 3 knots, those will be at the 10th, 50th, and 90th percentile of your distribution. Okay, and I'll do one example here where we looked at ICU admissions and our outcome was death or readmission within 48 hours of discharge. And we have 8 risk factors: age, diagnosis, Apache scores, heart rate, oxygen saturation, blood pressure, and FiO2. So the first thing to do is to look at the nonlinearity of age in this case. And so I use 3 knots. And so the 10th, the 50th, and the 90th percentile come out to be age of 39, the 50th, 64, and the 90th, 84. So those are where these are my knots in my spline function. And so this is just an example of how you then calculate what the regression coefficients are for the splines. And again, I won't go into detail. I think that's pretty straightforward. You can take a look at that. But the regression equation you get then can look pretty nasty. And this is what it would look like for our example here, where we have the either death or hospitalization within 48 hours of discharge. So we have our regression coefficients here for the Apache score, for worst FiO2, for the minimum oxygen saturation, the respiratory, and then we have our splines for age. And so this is would be how we would calculate what the probability is for any given patient, depending on their values for each of these variables. Then one other, or maybe I've got two more, I'll try to finish up here. It's what we call locally weighted least squares regression. This is a smoothing function where we do a linear mean or running mean or a linear function. How smooth it is depends on the bandwidth. So my example here is a bandwidth of 3. So to smooth, what I'm taking is the first 3 values of my variable, dividing it by 3. So that's my first point in the smoothing. Then for my second point, I would take the second, third, and fourth values, divide by 3. Then I would take variables 3, 4, and 5 and divide by 3 and so on. And so basically here, the larger the bandwidth, the smoother the function. So if I do this for, say, 4, where I have x1, x2, x3, x4 divided by 4, and then I'd have x2, 3, 4, and 5 divided by 4, and so on. And so this generally gives a pretty good idea of the relationship between two variables that's either not over smoothed or over fitted. And so here's a couple of examples where we've looked at the relationship between the 2-hour oral glucose tolerance test and BMI. So you can see that it's kind of hard to determine if there's what the relationship is just looking at the points by themselves. But if you do a lowest smoother, you can get an idea whether it's linear or nonlinear. And then here's sort of the same thing for 2 different variables for cardiovascular events, which are in the yellow. And so the axis for that is over here is the events per 1,000 patients. And so this is my locally weighted smoothing function. And then for change in GFR over time, this is the function that I get. And so you can see it's a pretty good representation of the trends over time for those 2 variables. Okay, and then finally, what I want to finish up with real quickly here is nonlinear models where we actually use a nonlinear function. That is, they're nonlinear in the parameters. And basically, this is a solution that or analysis where you iterate until you find a solution. And usually you need to provide starting values for the parameters. But here's a couple of examples of a nonlinear function that's nonlinear in the parameters. And so here's a real simple one where you raise e to the minus whatever this is regression. This is basically the regression equation with regression coefficients and the covariates. And the plot of this is an asymptotic function that will look like this. The second one is a 2-parameter Weibull function. And you can see that's much more complicated. This is more of a time to event function or survival function. So the example I have here is a nonlinear model of total renal volume with age. And so it turns out that my best model here was what is a four parameter logistic model. And so the four parameters are my asymptote. One is the asymptote as age goes to 0, and 2 as age goes to infinity. B is then the inflection where my curve is going to change from concave to convex, and then C is just a scale parameter. B is my primary parameter of interest because it's the age at where there's a change in the rate of increase or decrease in renal volume, and the expectation is that it occurs at puberty. So this is my model as I've written it. I think this is R. So you can see that it's fairly complex. And so I'm modeling the A1 and A2, the asymptotic functions, plus B plus C. These are fixed. The weights here are, I'm saying that age is nonlinear, and that A1 and A2 are random effects. I have to give my starting values, and then I'm here doing a subset of my total data. And so this is the results that I get, my estimates for my 4 parameters here, A1, A2, B is 12.29, and C is 2.17. B is the one that I'm most interested in because our expectation was that the change in the function would occur at puberty, and so that turns out to be pretty close. And so if I plot my data, this is what it would look like. The dotted lines are the actual plots for each individual. And then my regression line is solid with the 95% confidence intervals. And you can see then if I look at my parameter B, which I said, which is the inflection, you can see that it changes from what is it, convex to concave, where basically the slope changes, or the curve changes direction. So to end up here, our general and generalized linear models are used to look at the relationship of covariates to the outcome where the relationship is linear. If the relationship is actually nonlinear, then we can use, and what's used most often are linear solutions for that, which are polynomial regression, either integer or fractional, and splines, and then nonlinear models, where we use actual nonlinear functions. And so an important point that I want to leave you with here is when you have nonlinear models, that there's always, whether you do it with linear relationships like splines, or whether you're actually using nonlinear models, there's always a trade-off between being over smooth and overfitted. Overfitted meaning that you can, basically get a line that models every single point in your data, but usually you want something that's smoother than that, that gives you an overall indication of the relationship, of the nonlinear relationship. Okay, so I see our time is up, so I'll stop there. And if you have any questions, you can, we'll take a few minutes here. So the question is there a better way to avoid collinearity when choosing explanatory variables, including interaction variables, to include in a regression model? Then to calculate correlations between pairs, trying to of explanatory variables prior to running regressions, and also to watch for estimated coefficient sign switches resulting from including and excluding various explanatory variables in the regressions. So, so first of all, if you just do correlations between pairs of variables, that may not work because you, when you include covariates in a multivariable model, remember that they are adjusted for all of the variables in the model, so that if you have the correlation between two variables and you then add a third one, that could change the correlation or the relationship with the outcome variables with the other two. So that's not always a good way of doing that. Typically, if you start by putting the variables in the model, most software, I know Stata does, I think SAS does as well, will tell you whether a variable is collinear with another variable. And so you can then exclude whichever one you think is the one to exclude or include. If you do correlations between pairs of variables and you have, say, a really high correlation between two variables, that might, be an indication, as well. But I think that if you do have variables in your model that are collinear, usually most statistical software will tell you that. Okay. All right. Any other questions? Okay. If not, I see we're over time. So just to remind you that there's a recording of this that'll be released by the Georgetown folks, and they will also send a copy of the slides to everyone who's registered here. So again, I want to thank you for your time, and we will engage again next month. Thanks.